so why don't we go ahead and get started. My name's Dan Agnew. Appreciate you guys all coming out today to talk about simulation and camshafts. Didn't realize the screen was going to be so low, so you might have to stand up and back at some point to see, or all the good stuff will be down here on the bottom where you can't see it. I'm sure you can read that from the back, right? All the legal stuff. Okay, what we're going to talk about today, first, just a few minutes. These first few things are only going to take a few minutes, and then we'll get to the good stuff here. But a little bit of background about ACS. We'll talk about why we want to do this type of computer simulation on performance engines and vehicles. What 1D tools are available out there and what I use, how the models are constructed, and then we'll get into the meat of it with using the model for cam optimization, and then how to use the results in calibration, and then we'll wrap it up with some summary. My colleague Steve Ruiz, he's not here. He's the calibration guy, but he helped me with this, so I'll try and cover his stuff at the end. Okay, ACS. We are specialists in product development, calibration, computer-aided engineering, or CAE. Emissions compliance that's where a lot of the bulk of our work is, but then a lot of these other things have to support that to be able to be successful with emissions compliance. Operations and business strategy, both in the aftermarket and the OEM space. Typically for CAE, like what we're talking about here today, we're going to be working in valve trains, cooling, lube oil, structural, vehicle systems, like suspension systems and whole vehicle design. Our projects are most often confidential. Generally, people pay us to hide in the closet and do the work and let them know when we're successful. And for many clients, as a result of that, we're their virtual engineering department. Our clients are all big companies, small companies, but we're usually filling a space in that company with a skill set that they don't have or they don't have the capacity to do. A lot of diversity in our project types, concept, propulsion systems, that's a lot of what I do in the simulation world. Automotive, industrial, agricultural. Last week I was working on a locomotive engine, and this week I'm talking about race engines. So, and anything in between, or even smaller, weed whacker engines sometimes. And then a lot of the work, like what we're showing here today, is in the performance and racing business. Okay, why do we use computer simulations? Three big reasons: cost, time, and understanding. The initial investment in a model is typically going to be real similar to like setting up a new actual dyno test, but the facility and hardware costs, there's enormous savings. It still requires specialist people like us at ACS, just like a dyno and an engine builder, a tech. I mean, they're all specialists. You still got to have good people like that. And then we basically just need a computer and some software. I tell people I can do my work from anywhere. A lawn chair and a laptop and a beach, I can still get my work done. I don't need a lab. The time, the large test plans, like what I'm going to outline here today, you can do that much faster with these types of simulations. A typical dyno run, I mean, you might have a few days in setting up the base model, but then once you set it up, you can just run it fast. This particular design of experiments that I'm going to talk about today, I think that if I remember right, there was like 250 runs in it to populate the whole contour of what we tried to run, and that runs in just a few hours. One particular speed run might be 5 minutes. I mean, I can't even drink a cup of coffee that fast, so that's as fast as this stuff runs. And also very importantly is the understanding. We can get a lot more information for more complete and a deeper understanding. And if you think about this, I have an unlimited number of data channels. A lot of you guys that are dyno operators and test technicians, you're pretty limited by what you have for your budget or your facilities in data channels. I have how many? There's thousands, and anything you can think of in the model, and I'll show you in a few minutes, you can go tap on that and pull all kinds of pressure, temperature, fuel data. So the available tools, I'm not passing judgment on anything I'm showing here because they all have their place in this business. But I just showed what a sampling of what's out there. Some of these are very basic in their capabilities. Some of these are just basically a catalog lookup, and it's correlated to basic relationships. Some of them are actually based on gas dynamics. Some of these basic ones, they're pretty limited in their model complexity. The advanced simulation tools, where I put the GT suite, which is from Gamma Technologies, I highlighted that in the bottom. That's what I use. I've been using that since before it was even GT suite for almost 40 years. I think I was one of their very first users when I was at General Motors almost 30 years ago. But I would put that in the advanced simulation tools, and that's where the multi-physics comes in. And what I mean by that is that these models include lots of aspects of engineering: the flow, acoustics, the thermal, mechanical, electric, chemistry, controls, just to name a few. These basic simulation tools probably aren't going to have a lot of that. We also do a lot of hybrid electric vehicles, and that has a lot of electric componentry to it. These obviously have a lot of chemistry with the fuels. You got to burn the fuels. A lot of chemistry associated with combustion. Same thing with mechanical. You can build in the whole crank train or valve train into these models if you want to. You don't have to, but if you want to, you can. Acoustics, we can look at noise. I'll show you some examples of some of the components we do with that in a few minutes here. And then controls. You can actually set these models up, run them, populate a database, and then you can thrift that database down and basically run this as a real-time engine to feed a hardware in the loop or software in the loop type of control system. So you can simulate that engine to develop your calibration. That's a level of complexity beyond what I'm going to talk about here later, but that's certainly within the capability of a software like GT Suite. There's extensive detail for geometry and content, a lot of pre and post processing. I'm going to show you, if the computer gods agree with me, I'm going to actually show you some of the live post processing here. You can also run distributed computing. If your models get so big, you can run them up in the cloud and run all kinds of CPUs and run it as fast as your budget allows to rent CPUs in the cloud. And you can couple to other softwares like CFD, engine controls, emissions, thermal, things like Simulink or MATLAB you can link to. So there's a lot, I guess my message here is that there's a lot of tools out there. Depends on what you want to do with them and what you need and what your budget is. Obviously, the budget for something like Gamma Technologies or Realis used to be, some of you might remember the Ricardo Wave. Well, Ricardo spun off its software side of the company and renamed it as Realis. That's very similar to the GT Suite. But these vary from a few $100s for a permanent license to tens of thousands of dollars. I don't get to buy GT Suite. I have to rent it every year, and it costs a lot of money to do that. So. Okay, how is a 1D model constructed? Well, if I have CAD model available, that's always the best. I don't always have CAD model. When I do some of these locomotive engines, sometimes I'm literally out there with a tape measure or a yardstick measuring these things. I love doing engines that I can actually walk on and make measurements. And some of these are 70-year-old engines and CAD models don't exist. So there I have to get a little creative and basically build these models from just measured data. But if I have CAD data, that's awesome. I pull an air core from this model, and then with the GEM 3D is the preprocessor in GT Suite to take that air core, break it up into pipes and volumes and junctions and orifices, and then I take that, where'd my cursor go? There it is. I take that GEM 3D model and then I can discretize that into this other picture on the right, on your right, that's actually the GT Suite model. And all those little dots you see in there are some type of an object, either a volume or a pipe or an orifice. And that's actually the manifold submodel over there. And you can I kind of moved them around so it kind of looks like a dual plane manifold. Similarly, on an exhaust manifold, here this example, I already have the air core. The client here actually gave me the air core instead of the CAD model. But same thing, I run it through the preprocessor, turn it into pipes and junctions, and then from there I turn it into the GT Suite engine or submodel that goes in the engine model. This is an example of a muffler. And depending on what the project, if the project is where the customer wants to actually look at noise, then I put a lot more detail into it. Like this model has a lot of sub-volumes in here. And you can see by the time it gets to the GT Suite, or the GT Suite model, every single one of those dots you see there is a volume in the muffler. And I kind of need that detail if I'm interested in noise. If I'm not interested in noise, just looking at back pressure, then I can make this this model a lot more coarse, and then it'll run faster. Instead of minutes, this model there's a lot of math associated with calculating all the interaction between these volumes. So this might take 20 minutes to run instead of 5 minutes to run. So. Okay, the valve train, there's a module within GT Suite called Valvedyne, and this is it used to be standalone, and we were just talking about this before. We wish it still was kind of standalone, but it's not now. It's embedded into GT Suite. You can either embed this inside your engine model and actually run the valve train live inside the engine model, or you can run it standalone, create your lift profiles, and then take the lift profiles and put them into the GT Suite. For some of us that have the luxury of a Billy Godbold to create profiles for us once in a while, then we don't necessarily need this. But this is how these models are created, where we start with the geometry. I can flip that into basically a flat model of intake and exhaust with all that geometry, and then if I'm going to go look at the system model, and I can actually put these together into a whole camshaft assembly, when you're getting more interested in some of the dynamics, doing spring design and some of the stiffnesses of the components and interactions between the profiles, then you're going to want to get in to do more system analysis. If you only need some kinematic analysis, well, then you don't really have to go any farther than this basic VT design model. But if you want to get in to look at some of the dynamics, then you got to build the system model. And then when you get into the engine model, all this goes into the engine model. And for this example, the engine I used was basically LS7 based. I know the LS7 is not a variable valve train, but that's kind of the base engine architecture. And I just wanted to create a demonstration of what this can do, so didn't necessarily need a real engine. I pulled an aftermarket based dual exhaust system. You can see, here I'll walk through. It starts at the air intake. This is the air cleaner, goes through the manifold, and then have the 8 cylinders here. And then the exhaust manifold goes, in this model, it goes through a catalytic converter and then through a kind of a dual path muffler, a single but a dual path muffler. And Billy was kind enough to generate some cams. I didn't have the OE cams. We talked about kind of what I wanted to do with this demo, and he generated some pretty realistic profiles for me. So thank you, Billy. Okay, the process. This is where I also had an interesting discussion with Billy, because his process is a little bit different than what I was trying to do here. But we end up at the same place, and it depends on what kind of resources you have available. So you want to start with, if you're doing cam optimization, you got to look at what parameters do you want, what parameters do you have available that you want to change. And in this, I looked at the lobe center timing, I looked at peak lift and duration. Those are the things I limited myself to with this DOE. Doesn't have to be limited to just that, but that's what I did. You have to figure out your reasonable limits, and you can go a couple of different ways here. If you have a valve train or a camshaft profile design guy for you that can crank out a whole bunch of profiles in a hurry for you that are realistic as far as their lift, duration, acceleration, velocities, all that kind of stuff, and can create a whole bunch of profiles for you in a hurry, well, then you can just run those real profiles in here. If you don't have access to that, then you can use GT Suite. It has some built-in scaling factors where I varied lobe centers. You don't have to scale. You can just move them back and forth. But with lift and duration, I can actually apply a multiplier for it. So I can take the duration and I can make it wider. I can take the lift. I can make it more or less. But you can guess that you can get yourself into trouble with, especially you can get yourself in trouble with Billy if you have too much lift, because I'm going to want more lift and less duration. Well, that's going to make his job tough. So you have to look at the results of this and say, does this make any sense? And if you can kind of bypass this scaling stage in this DOE that I ran, and if you have a lot of those profiles, well, you can just run those and sweep them back and forth with your timing. And if you don't have access to those, then my message here is that, well, you can just run GT Suite, but you may end up finding what GT Suite likes is not a realistic profile. So then you got to go back and talk to your valve train guy, and from that result, tell him, well, GT Suite's telling me I want more lift and less duration. Do the best you can, get me as much as you can in that direction. And then from that, you can optimize, run that, you can optimize the timing of it, and then you send those VVT tables to your calibration guy as a starting point. And just zooming in from that engine model on the cylinder, this is where those two little things there that look like orifices, that's basically what they are. What GT Suite treats them like is a variable orifice. So and then if you look at the input window, the cursor shows on my screen, but it's not showing here. Anyway, okay, lower left here is the intake profile. Lower right is the exhaust profile. But those are the tables that you actually put in there, and you can pull those right from software like what Billy generated with those text files. I just cut and paste them in here. I retime them, and then put them in there the way GT Suite wants to see them. And then when I run the model, and this is the starting point, on your far left here is the power curve, the torque curve. These numbers are pretty close to what I see published for an LS7, so I know I'm kind of in the ballpark, but my engine's a little bit different than a real LS7, so I'm not too concerned. I have a full exhaust on this, so it's probably not going to make the kind of peak power that published engine would. But I think what I like to look at also, and if you've ever seen any of my presentations before, you know that this is one of my favorite plots, is where I overlay mass flow through the exhaust and intake valve. I overlay that on the camshaft profile, and you might not be able to see this from the back because it's pretty fine line. But what this is telling me, the dashed line is actually the flow, and what you can see on the exhaust profile is the mass flow. It shows the blowdown, and then it kind of falls over, and then as you see the piston comes up, it just kind of finishes pushing out the rest of the exhaust. On the intake, you don't really have that big blowdown when you crack an intake valve, but at high piston speed, the piston is what's actually creating the draw for the air through the intake valve, and so you see that peak mass flow is later in that event. So for you port flow bench develop guys, there's a message here. It says that's where you should be spending your time developing your ports. You know, the lower lift on the exhaust, the higher lift on the intake. And this demonstrates why. And these were the baseline The plot on in the cam profiles here, the plot on the left side there is the base, the power point, and the one on the right is the torque point at 4,800 RPM. And you can, what the signal to me is, if you look at that intake profile, the mass flow versus the cam lift, it's a lot different shape. The exhaust it's kind of similar, so this is telling me that maybe where I started, my starting point isn't so far off. But the intake looks like it's a lot off, because you have a lot of reversion. Where that intake valve closes, you see that big spike, negative spike. That's telling me I have a lot of reversion, so that's telling me my cam's not timed right for that. This is the kind of output. This is a screenshot of the GT Suite output. It's called GT Post, where I'm looking at this optimization. And so I have 6 variables that I varied in this DOE. Intake lobe center, intake lift, intake duration. The intake lift and duration, those are scalars. So I start at 1, I scale them, I go down to 0.75 up to 1.25, I think went to. Same with exhaust lobe center, exhaust lift, exhaust duration. The set here on the left is the peak power, 6,400 RPM, the baseline. And on the right is where I optimized it at peak power, 6,400 RPM, and that's what I found. And let me try and see if this works here. I'm going to swap back. Okay. This is actually the live GT Post. And you can see here that there's the six charts that you just saw here. They're in a little bit different order here. But what I like to play with here is I have these slider bars where I can look at, this is exhaust lobe center. So as I'm moving exhaust lobe center around, it's going and interrogating the database that GT Suite calculated. And you can see how it affects all these other ones. Same thing with intake lobe center. If I move intake lobe center around, so this gives me an idea of the sensitivities of each of these. If you look down here in the lower right, where I'm looking at the exhaust lift multiplier, you can see that's pretty flat. So that doesn't really have a big response. If I'm looking up here, intake lobe center, well, that's got a lot more slope to it. I have a lot more response. And in this particular case, the y-axis is brake torque. You probably can't see that from the back, but so, oops. So as I always do this. So as I'm varying that, as I'm varying intake lobe center, you can see there's still the exhaust lift multiplier. That doesn't change a whole lot. So that's telling me that, okay, that's not a big calibration knob in trying to develop here. So that's a pretty powerful tool for me. So I'll sit and I'll play with this until I think I got these about optimized. And then I'll go and look at what these numbers are. It actually gives me a summary report, so I don't have to do this all manually. But and then I can go plug those back in the model again and rerun it and see where I'm at. And then I can go to Billy and say, like I thought, I want more lift and less duration, so please make that work for me. Okay, let's try and go back to PowerPoint here. Okay. So you can see in this what I was showing you was the peak torque optimization. This page here is the peak power, and on the left here you can see how big a slope it is. Intake lobe center was pretty sensitive, a lot of slope to that. So that's telling me something that's something I really have to pay a lot of attention to. Exhaust lobe center timing is obviously real important too. Duration has pretty good slope to it. Intake and exhaust duration, intake lift and exhaust lift, not so much. It's a lot flatter response. Here's trying to optimize at 4,800 for peak torque. Same kind of idea. Here at peak torque, from where I started at, duration looks like there's a lot of slope with duration and lobe center on the intake side. Some slope with the exhaust lobe center and exhaust duration. And then you can see where I ended up was quite a ways off of where I started for peak torque. So it tells me that my initial guess for cams was pretty good for peak power, but it was way off on peak torque, which is the whole idea behind why the OEs are doing variable valve trains. So they don't have to compromise. They can get the best of both. If you already have a profile and all you have available to you, you already have this engine, it's a variable valve timing engine, and all you can do basically, you can't go throw new cams in it, but you can sweep the timing. Well then, what I did is I fixed those scalars at 1. I didn't change those, and then I just reran the DOE, only varying timing, and so I get some different results obviously when I can't vary lift and duration from my base starting point profile. But I went through the same kind of exercise, and you notice here the intake lift, exhaust lift, durations, they're all fixed at 1. You know, from the baseline to the optimized. All I could do was vary